Welcome to this presentation on single-use delegatable signatures based on smart contracts. My name is Stephan Krenn and this is joint work together with my colleague Lorünser from AIT. This work was partially funded by the European Commission through the CyberSec for Europe and slot machine projects and by the Austrian Research Promotion Agency through the FlexPort project. In the delegatable signature scheme, we distinguish the following types of actors. We have users holding secret signing keys, and we have verifiers knowing the corresponding public key. Furthermore, we have delegates. Delegates may or may not have their own key pairs as well. Now, users are able to derive so-called delegated signing keys from their signing key and forward them to the delegate. The delegate can now use these delegated signing keys in order to issue signatures on behalf of the user. The verifier can then check the validity of those signatures using the user's public key. The security properties that we typically require are as follows. First of all, correctness requires that if all parties behave honestly, then signatures should also always verify. Secondly, unforgeability requires that no party, neither knowing the user's signing key nor a delegated key, should be able to generate a signature that is accepted by the verifier. Typically, we also require transparency, saying that the verifier must not be able to identify the originator of a signature. So from a verifier point of view, signatures issued by the user and by the delegate should be indistinguishable. And then the literature defines several other security requirements, such as accountability or immutability. The property we are concerned about in this paper is one-timeness. So we want to make sure that the delegated key can only be used a single time and becomes invalid afterwards. Obviously, such a solution cannot be based fully on software because you can always copy and re-execute a software program. And therefore, a whole body of work has been done on so-called OneTime Programs. And in order to realize such one-time programs, usually trusted execution environments or one-time memory or other special purpose hardware are assumed. A different approach was taken by Lorünser et al. A few years ago, who proposed one-time programs based on quantum properties. So their approach is as follows. The user takes his signing key, the signing algorithm, and encodes this into quantum states. Then this quantum state is transferred to the delegate using a quantum channel. And in order to generate a signature, the delegate now executes this quantum program on the message and obtains a classical signature. The nice thing now is that the execution of the program requires to measure the quantum state, which causes a change of the system's state, and therefore the quantum algorithm cannot be re-executed. Let's now look at our construction. I'm going to show you only the basic construction. More details and extensions can then be found in the paper. We now consider the three parties, and we assume that we have a blockchain that supports smart contracts. So in order to derive a delegated signing key, the user samples a random value x, and it computes y as the hash value of x. The preimage x is sent to the delegate, and then a smart contract is put into the blockchain. The smart contract defines the following. First, it fixes the values of y and the user's public key. Furthermore, it defines the state as an empty string, and it defines the following condition. If somebody is able to send a message and a zero-knowledge proof of the preimage of y, then the smart contract should check whether the state is still empty, and if this is the case, the state is updated to the message to be signed. Now, if our delegate wants to sign a message, she just sends the message to the verifier, and also to the blockchain network, together with a zero knowledge proof of knowledge of X being the preimage of Y. The blockchain checks the conditions in the smart contract, updates the state of the smart contract, and the verifier can now check the correctness of a signature by simply checking whether the state in the smart contract corresponds to the message being signed. The nice thing about this construction is that now signing again changes the state of the smart contract, and therefore reuse of signing rights is avoided. Furthermore, in this construction, our delegate does not need to own any long-term key material. The question is now whether this approach is by any means practical. And in order to answer this question, we implemented our smart contract in the Solidity programming language for the Ethereum blockchain. You can see the smart contract here on the right-hand side. And our evaluation shows that all transaction and execution costs are in the area of a few $cents to be executed. So the most expensive part is the constructor of the smart contract, which costs about 500,000 gas, and all the other activities are around 30 to 70,000 gas. And in particular, this constructor could be amortized by reusing the same smart contract for many signatures and not setting up a new smart contract for each signature. As I mentioned, the construction I showed you only considers the very basic functionality. In our paper, we also show how to define designated delegates and how to achieve accountability of our delegated signature scheme. In both those cases, the delegate needs to own a key pair. Then we show how to extend our construction to n-time signatures. We show how to increase the privacy, because the plain construction reveals the message to be signed to the blockchain network, and basically just by hashing, this can already be overcome and privacy of the construction can be achieved. And we also show how to get immutability, which means that the user can predefine blocks of the message to be signed, which cannot be changed by the delegate. Future work will now include the formalization of our approach in order to get formal security proofs, and we're also going to investigate whether this approach can be used in other scenarios beyond basic signature schemes. And with that, I would like to end my presentation, and I'm looking forward to discussing with you during the ARES conference.